Okay, so thanks, Michael, and thanks for the organizing committee for the invitation. Yeah, my name is Moha, and yeah, actually my full name is Mohammed. I go by Moha or Mo, wherever works for you. I'm good. Today I'll be talking to you about data assimilation in hydrology and mainly really stream flow forecasting. Before I start, I'd like to give some shout out to a bunch of my collaborators who help out with this project. And these are, I put them on the screen up there. So to start with, let's see if I can move this. Yes. Okay, so this is my outline. I'll begin with a couple of slides of motivation of why we do stream flow forecasting. Now, just so my talk would be slightly different than what you've seen, for instance, from Francois and Aneta. It just I won't have a lot of history about stream flow forecasting. It just for the simple fact that data assimilation in stream flow forecasting is something very recent. There have been a lot of calibration studies in the past, but really operational data assimilation for stream flow it's just very recent. So. In fact, some of the things that I'm going to show you here in section 4 are quite new, and I'm introducing them. For instance, the localization that we developed for this kind of application. So after the motivation, I'll talk about the stream flow model. Essentially, it's a lot more than the stream flow. This is a warfighter model, and then the data assimilation tool that we use. We use to interface the model and the DA together. Essentially, the meat of my talk is in section 4. There are a lot going on over there. There are some theory stuff, and but it's something interesting. And at the end, I'll show some results from the application that I have in this study. And again, disclaimer, sorry if I'm drinking coffee because I think I need it. Okay. So so as for the motivation here, so I'm looking here at Hurricane Florence. So this is a hurricane that hit the Carolinas mainly in 2018. You can see here in the movie, this is essentially the eye of the hurricane moving in, approaching to the east coast of the US as it made landfall. So this kind of hurricane started as a tropical wave of the west coast of Africa, and then it developed into a tropical storm before making a landfall as a Category 4 hurricane in, I believe, on September 2014 in September 14, 2018 in the Carolinas. So the winds that actually this hurricane produced, the speeds went up to almost 150 miles per hour, which is a ton of wind. I mean, unfortunately, as for much of the hurricanes that we see here in the States, but this hurricane wrecked, left a lot of damages, and the estimated wreckage was around $25 billion. It was massive. That the flooding magnitude, the freshwater flooding that happened during and after landfall was estimated that it was actually larger than what we observed for Hurricane Matthew and Floyd together. And here I'm showing here in this map just the precipitation rates that some of the areas got during the hurricane. And there are some areas where some towns, some small towns, especially in north and the northern part of southern Carolina, got more than 35 inches of rain, which is really a lot of rain. Here in the next slide, I'm going to show you just a movie, which is like a 4-minute movie. So of how of some of the damages in a single town in North Carolina. So the movie has sound, so hopefully it works. Can you hear the sound, by the way, of the movie?
I think no. You can try.
I'll stop sharing. I think I need to tickle something when I share the screen by accepting. Yes, share sound. Yes.
Okay.
Okay, and this one. because it's definitely better with sound. Okay, tell me how about now?
Yes, yes.
Okay, awesome.
There's
Okay,
sound
so
now. Yeah.
okay, I'm gonna let it run, and yeah, we'll proceed afterwards.
You can see inside the house, and you can see waves that have punched through the back side of the house. So you see here the amount of rain that's coming in. The precipitation is just, a ton of rain. That most of the flooding that you see is actually a freshwater flooding. So the rivers essentially are being flooded, and the water drains over the banks and into the cities, into the towns, and that it creates massive damage. That looks like a wall cloud right there.
Yeah, again, so this is all freshwater flooding into the city. See, it's how much it's covering from different stores here. This is not like, a sea or something. This is a freshwater flooding. Okay. Okay, so after we've seen that,
Again, I'm going to ask the question, why stream flow forecasting? I guess the answer is very clear right now. With the Hurricane Florence, 50 people have died. So saving lives, if there's a way that we could predict these kind of flooding events that happened during the hurricane, that would be great. We could obviously help limit the damages if we have some kind of system that gives some advance warnings for residents. And, it would be nice, the priority is to save lives, but, protecting infrastructure is very important. This is the impact of these kind of things is not only, infrastructure wise, but it affects the social life as well. Many people in that area or in states like Louisiana during the hurricanes, they lose their houses, they end up homeless. It's a life-changing kind of scenario that happens during these things. I mean, look at the town. There's the town is essentially entirely damaged. Repairing all of this takes years, if not decades. So, and that's what we're hoping to do in this project here. Now I'll try to stop like after every section, I can see the chat or the questions. So Michael, please let me know if there are any questions that come up during my talk.
Yeah, sure. I'll read the questions to you. Yeah.
Awesome. Thank you. Okay. Now, before talking about the model, I just wanted to mention some facts about these hurricanes. 2020 was the most active season, and you wonder, how much worse this 2020 could have gone. So in the US, we had 12 storms that hit CONUS or continental USA. One important thing to realize that on top of all the massive wreckage and the damaging and the flooding that happens, in fact, one of the lethal consequences of the hurricane happens after everything is said and done. So for instance, here's a stat here. So since 2017, at least 39 people have died following the storms, and that's because of carbon monoxide poisoning from improperly used generators, which is sad. 2021 Atlantic hurricane season officially began last Tuesday, so this week. And as a fun fact, so the National Hurricane Center already assigned 21 storm names for this season. As you can see, these switch between female and male names. So let's see how many we get for this season. Okay, so jumping into the model. So we would like to solve this problem. We will start by the model. We'll start to write some equations, model the stream flow. And afterwards, we will hook that system with data assimilation. We'll try to get the best out of the data assimilation and the model in order to provide stream flow predictions. Okay, so what is WARFIDER? So WARFIDER is NCAR's weather research and forecasting model for hydrological modeling. So in the US, WARFIDER is nothing but the research compartment of the National Water Model. So the National Water Model is what the government uses essentially to predict this kind of events. So WARFIDER is a community-based system. It can be used for many different things. Most importantly, it can be used for predicting precipitation, soil moisture, snowpack, groundwater, stream flow, inundation. And that could happen on many different frameworks. For instance, you could work with regular grids, catchments, water channel vectors, and this is what I'll present today, mostly a stream network, essentially, or reservoir polygons. There are many different configurations for the model. With WARFIDER, we could also provide reliable stream flow prediction across scales. So going from zero order headwater to big catchments, essentially, with many different streams. And then we can model on different time scales, going from minutes to seasons. And once we couple that with the land model, we end up with a robust framework for land atmosphere coupling. You can do many studies with that. People who are interested, or maybe people who are familiar with that, you can get a lot more details from our WARFIDER webpage here. There's a lot of training, helpful material from online sessions, Jupyter Notebook lessons, different applications, online exercises, and some training with Docker Hub. Okay, so speaking about WRF Hydro, so these are the major components of the system. So starting from the weather forcing engine, and that could be any model. For this kind of application, it's usually WRF or the weather forecasting model, which is usually run on a 1 to 4 kilometer grid. So from that, we go down to NOAA or NOAA-MP. So NOAA here is a land surface model, and it simulates a number of different processes for the land, for instance, soil moisture, and that can be liquid or frozen. We have soil temperature, skin temperature, snowpack depth, snowpack water equivalent, water content, energy and water fluxes, a bunch of different things. And you could also use the MP version of it, which is comes with multiple parameterization, and that's a key for land atmosphere interactions. Now, this land model is two-way coupled with a terrain routing model. So essentially, the infiltration excess or the ponded water depths, the soil moisture, these are subsequently disaggregated from the land surface model or the LSM, and then they are essentially passed to the subsurface and overland flow terrain routing models. From there, we build what we call the catchment aggregation, and for the U.S., for instance, the national hydrology dataset or the national hydrography dataset essentially aggregates around 2.7 million reaches in the continental U.S. And then from there we go to a simple channel reservoir routing model, this study will essentially focus on this part of the problem. Obviously, we are coupling with some data assimilation. You can do many different things. You can do some web mapping services. There are many different areas for evaluation and calibration of the model. There are many different. I'd say NOAA has been, or NOAA-MP have been tested like a lot in online, offline, and in operational settings. WRF Hydro hasn't been so much tested in terms of data assimilation, but there have been a lot of funding lately, especially from USGS, which is the US Geological Survey, to conduct these kind of data assimilation studies with WRF Hydro. Now, in terms of the model physics here, as I said at the beginning, there are many different physical configurations of the model. So these are the different components that we talked about. For instance, the land surface model, you could, you could use either NOAA or the multiple parameterization part of it, or a third option, which is really I'm not familiar with. Now, the national water model configuration at the moment is using NOAA-MP. And the others, they have many different physical configurations, which I'm not going into the details for that. For instance, the conceptual base flow model. So this is a model that describes how the groundwater essentially behaves under the surface. So this is very conceptual at the moment, but I've seen some latest developments where I guess the WRF Hydro model developers are planning to replace that with ModFlow, which is the USGS groundwater simulator, a lot more sophisticated than what we have at the moment. And for the channel routing, this is the Muskingum-Kunj model is the most famous and the most tested, I'd say, out of the rest of these physical configurations of the model. So WRF Hydro has been used quite effectively for streamflow forecasting. Again, not so much for data assimilation. And just to show you what's the benefits of the model and how far you can take the model. There's also a movie here, which is showing you essentially the streamflow over the last year, or 2019, 2020 water cycle. The units here are in CFS, or cubic feet per second. And you see, as you go into reddish or purplish color, so this is more, higher stream flow. So the main river here is the Mississippi River, where you have the most of the action happening. Now you will see here, so we are around November, as we usually there is higher flow in the Midwest area, and as we go into the winter, you can advance this a little bit. Sorry. So we are in October. Yes, November. As we go into the winter seasons, you will see that the stream flow would increase, and as you can see in the eastern portion of the country, following rounds of precipitation events. Yeah, let's see down. The stream flow is increasing quite a bit here in this region, and then as we get into the February, March, April, kind of see how much high flows are seen in this area. Yeah, as we get into the spring, into the kind of March, April, May area, I'll see a multiple spring storms, downstream across the Mississippi Valley, producing widespread elevated flows, which you can observe now. Now, as we go into the summer and the fall, we see some tropical cyclones affecting the eastern coast of the country. Now, also there's some action happening in the Washington area here in the northwestern part of the country. One thing you could notice here that the highest flows are happening very much here and on the eastern side of the country, and mostly drought conditions are persisting in the Rockies and in the desertic areas of Nevada and New Mexico and Utah. Okay, I think it's enough with that. As we go into the summer, the flows decrease back again, except for, in the Mississippi Valley. But yeah, that's that. And now all of this model and, is being calibrated using some streamflow gauges. And I'd like to show you that as well. And for that, I'd like to share a different screen if I can. Okay, let's see if I can do that correctly. Okay, essentially, so these are the gauges that provide data for the model and for the data assimilation for assimilation purposes. So you can see my our website here, our page with the map.
Yes.
Okay, awesome. So this is a USGS webpage which provides stream flow information about from gauges installed on different streams and rivers across the country. For instance, we could let's see. For instance, we are working. If we could look at North Carolina, for instance, we can zoom in here and look at different gauges. For instance, let's see. So this is the color essentially determines how high the flow is. So let's try to find a high flow. So let's go to this gauge here. You could look at different, a summary of the stream flow here. We could look at hydrograph, which is nothing but a time series of how the stream flow or the discharge in the region looks like. And this is like historical peaks of in that gauge. This goes all the way back to, I can't read the number very well, but yeah, you'd see that some gauges are, you go back, the date all the way back, tens of years in the back, but some of the gauges are pretty recent.
And this is actually one of the projects I'll talk about at the end of the study. That USGS is interested in, gauge placement, like where can we put the gauges so we maximize the information from them. So there is a ton of things here. You could look at the flooding map. So what is flooding right at the moment in the country? Again, in the Texas area, in the Mississippi Valley here. Look at the drought. There's a little bit in the Rockies here, west of Colorado, and mainly the desert part of the country. This is where we get our information for data assimilation. Yeah, if you're interested, you could look at that. But you could create animations about the streamflow in the past, and this is quite a very useful tool that. Oops, sorry. That aids essentially the hydrologists when working with the streamflow. Okay, do we have any questions, Michael?
I don't see any.
Okay.
I guess I can ask a quick one.
Sure.
So are the observed variable the same as what your model? So the model have water amount or flow rate? Is that right. The same thing with yeah?
Yeah, that's actually a very good question. So in fact, the model, the Warfighter model is exactly streamflow. So and the gauge is giving you also streamflow. So but there is you don't really need to build kind of a forward operator or a function to relate your state variable to the observation. So it's just simply an identity, which simplifies a lot of things in the implementation of the data assimilation framework.
Great, thanks.
Mm-hmm. Okay, so if no more questions, I can proceed and talk about the data assimilation tool that we use here, and that's DART, or the Data Assimilation Research Testbed. I'll talk a little bit about DART, and then I'll go into some details about the math. So DART, if you're not familiar with it, so this is a community facility for Ensemble DA. It's developed and maintained by DARIS, which I am part of at NCAR. The nice thing about Dart, that's obviously it's free, it's flexible and portable, well tested. We distribute the code for Dart on GitHub. If you check out this page here, we support a lot of different models. So we go from really toy models like the Lorenz's that you've seen obviously in this summer school, to huge models like to air system models, and mainly the community air system model that is distributed by NCAR. So here on the right, you can see inside the cloud, not all of the model, but the majority of the models that we support in Dart. And these are only the big air system models, rather than, I'm not mentioning the toy models in here. And obviously Warfighter is one of them, which has been recently added, given the work that I am showing you here. Observations, assimilate real, synthetic, and different kind of observations. It's called testbed because it's mainly used for research purposes. So we go from theory-based to different kind of applications. There are some algorithms that support nonlinear filtering and non-Gaussian approaches as well. And there are some coming in the pipeline right now. Many different enhancements for the ensemble filtering theory. For instance, we work with adaptive inflation, localization, and I'm sorry, my clock is chiming, so it's 7 o'clock here, so you should hear 7. There is a lot of teaching that happens. We conduct a bunch of different tutorials. And Dart is, as I mentioned, is widely used. So it's used by almost 50 UCAR member universities and more than 100 other institutions and universities around the world. We always encourage and look for collaborations with different institutions. So if you are interested, please let us know and we can work together. If you want to look more into the details of Dart, so this is the website and the documentation is supported here.
this other website. So some characteristics about Dart. As you've seen so far, except maybe for Michael's stuff yesterday, all of the algorithm that you've seen is where they assimilate all the observations at once. So you have this X5 matrix or the transformation matrix where you put essentially all the observations in there and you multiply it with your anomalies and you get an analysis. Dart works differently. So it assimilates the observations serially, so one after the other. And that, that's could be nice because, it avoids the need for inverting matrices. It's simple because you're working only with scalars and, it helps with parallelizing your code. And theoretically, assimilating the observations serially is equivalent to batch assimilation. So if equivalent to assimilating all of them at once, except if you localize. But hey, I mean, localization breaks everything. In fact, if you think about it, localization breaks Bayes, from the beginning. So, what to do? You have to live with it, I guess. So on top of a serial assimilation, also Dart applies this kind of two-step least square updating scheme, and this is what you see here in the animation. So there are three members in here. You first find the observation increments. So you found essentially you calculate the observed ensemble and you compare it with the observations. You find some increments and you take those increments. You regress them just by linear regression back to the state, and you move forward that way. I'm just showing the equation here if you're interested. So this is the observation increments. You regress them on the state, and then you apply that. And the alpha we'll talk about it is just here a localization coefficient that goes between 0 and 1 to limit essentially the update on the state variables. So some Dart flow and functionality. So as I mentioned, we work with different kinds of observations. So we take the source data and we convert it. We have different converters for many kind of different observation formats. We put them into observation sequence files, which Dart work with. And then, if you start with a single model instance, you generate an ensemble. And we've been recently putting some effort on representing dealing with the representativeness errors in the observations. And, as you can see the flow here. So if you have an initial ensemble, you maybe need to inflate a little bit, and you can see here the uncertainty increases. We get the observation, we apply the assimilation, you see the footprint of the observations there, and then you integrate forward in time. We have a bunch of diagnostic tools, to calculate the different, whether your assimilation works or not. And I'm just showing here, if you subtract the analysis from the pre-assimilation, you see the impact from the observations essentially. So that's about Dart. And now let's get into the model and data assimilation configuration in the system here. Now, are there any questions, Michael, before we go into this section?
No. Okay. I think I can go ahead.
Thank you. Okay. So this is the model domain. So again, to reiterate, we are interfacing Dart with WRF Hydro. And we use a HydroDart, which is essentially a very detailed Python toolbox that connects these two things together. And these can be found on GitHub as well. So what you're looking at here is a regional subdomain of the national water model. So this is the domain that we're working with. And as you can see, we don't have grid cells like any other model. We're working with an irregular unstructured grid here. What we are trying to find, we're solving, the physical equations on streams or reaches, as I refer to them here. And these are nothing but the rivers, essentially. So in the domain, we have around 70,000 reaches. And from the data I've shown you, so we have around 107 USGS gauges in this domain that we assimilate, and we assimilate every hour. Now the gauge provide stream flow information every 15 minutes, but we can do some super obbing here to assimilate only every hour. Now it's useful to assimilate more frequently when the event starts happening. But in this study, we stick to 1 hour. Obviously, doing some sensitivity to the frequency of observation and time could be very interesting to look at. So these are the major rivers in the domain. The thicker or the redder the stream or the river is, that means there is a higher flow happening. As you can see, it's mainly close to the coast where the hurricane was approaching and dumping a lot of water in there. As for the assimilation, so we used an EACAF or a square root ensemble common filter with 80 members. Now, just for the configuration, so remember from the different physical configurations I showed you, here we are looking only at the stream flow and the groundwater bucket. So that we have essentially we're estimating, we're using stream flow observations, and we're trying to adjust these 2 variables on top of many other things, but I'd like to focus on these two things here. And for the configuration, so we run offline here the full model or the upstream kind of components, the atmosphere, the land, and the overland stuff for almost 8 years in here, and we start doing data assimilation. We do data assimilation over a month period, and remember the hurricane or the landfall happened on September 14th. So we get the output from this offline run, and that's like a fluxes into the groundwater bucket model and the reservoir here, and from there we do some kind of modeling. We interface that with Dart using the USGS observations, and we play with the system. Now we realized when we were working with that working with, for instance, here with a single flux here into the bucket model or a single flux into the channel really make the system it limits our capabilities. You don't get enough variability when you do that. So what we realized that we really would like to perturb this flux that's coming here, and we work essentially with a parametric noise model in order to create an ensemble of forcing both to the bucket and to the channel model. And this is what I'd like to mention here. So we apply some Gaussian perturbations to the boundary fluxes in order to increase the variability in the stream flow and the bucket models. Not only that, but also we create some variability in the model, just like what Annette was talking about before. So we have a different kind of parameters in the model, and we perturb these parameters. And I'm referring to this as a multi-configuration approach. So each member is running with a different configuration of a channel. And we have 6 different parameters here. So like the top width, bottom width, different Manning coefficients. All of the members have different values for these parameters, again, in order to create some realistic model variability. We don't estimate these parameters, but we keep them uncertain, because really these are uncertain and we are not sure how the channels are looking like. And as you can see, this is a compounded channel, so it's not like one level, but rather a 2-level channel in here. And we use some kind of uniform perturbation to get these ensembles for these parameters, but with some physical constraints. For instance, the bottom width cannot be larger than this width here. The same goes for T, cannot be larger than TCC, just to make sure we're working with a physically or nice looking channels. Now, the other thing I'd like to mention here before proceeding, so multi-configuration is not to be confused with multi-physics, which you see perhaps sometimes in the literature. So multi-physics really happens when you work with the ensemble where each member is actually looking at different physical equations of the system. For instance, as you see in my previous slide, you run with a different physical, like PDEs, for instance, with different members. But here with multi-configuration, the physics are the same, but rather each member is using different parameter values of the model. And this is definitely simpler than, much more simpler than multi-physics. Okay, so let's start with one of the main enhancements that we're introducing here for the data assimilation system, and that's localization. So you've heard from Gary, you've heard from Laurent, you've heard from a number of different talks about localization and why it's important, especially when working with the small ensemble sizes. A localization factor here is alpha for me. Again, it's between 0 and 1. It's kind of limiting the update on the different state variables. We don't take the entire step, the entire Kalman step, but rather some part of it. Just like what you do in optimization or steepest descent or Gaussian-Newton, you always have this kind of factor that makes you jump slower in your optimization. Now, a very important thing here that localization is usually introduced, to mitigate spurious correlations, because when working with small ensembles, you overestimate your correlations most of the time. But the localization we're introducing here, it also mitigates physically incorrect correlations between unconnected state variables in the river network. So what does that mean? So this is the localization that we've built essentially. You can see here, I'm showing an example from 5 different gauges in the domain. And you see that, for instance, for this gauge, the state variables that will be impacted are these guys here and, some of them downstream. This is for instance, 100-kilometer radius, and this is for a 200-kilometer radius. And the color here determines how much weight, or essentially what's the value for alpha that will be impacting the assimilation or the update step. And this is computed by some correlation function, which happens to be here Gaspari-Korn. Now, some characteristics about this localization. Most important one, in my opinion, that the flow of information only travels downstream. And that's why you end up with these tree-like shapes. Downstream from the observations, you only update really the states that are downstream. So you don't go upstream anymore. And because the size of the basins or the catchments is different, so the total number of closed reaches depends on the size of the basin. For instance, here, when we went from 100 kilometers to 200, you see that for this gauge or the diamond, you added a lot more state variables. But if you look at this triangle in here, not many more state variables, just because the basin in that region is just smaller. Another crucial thing is that the observations in different catchments, they do not have common close reaches. So look at this basin, for instance, or catchment, and this one in here. This observation can never impact any state variable in that catchment, just because these are 2 separate catchments. When you do, for instance, like regular localization, and you have an observation here, you will work with a Euclidean distance based. You will end up with a circle where you can have reaches from 2 different catchments, and that's physically incorrect because these things do not talk to each other. Now, we wanted to check if that if regular localization, as I said, like the circle or the Euclidean-based localization work, does it even work? So here in this table, I'm comparing the ATS with 100 kilometer to the regular localization with different localization length scales. So 20 kilometers, 10 kilometers, 5, 2, and 1. And I'm looking at different metrics. So I'm looking at the prior MSE, posterior MSE, prior bias, whatever. And as you can see that in most of the cases, actually in all of them, ATS localization significantly better than the regular localization. And I think if you were following what Michael was presenting yesterday, it happened that, for instance, I could not run any localization more with a regular localization more than 20 kilometers. It's just because it breaks the physics there, because you are trying to correlate 2 things that are they follow different regimes essentially. So beyond 20 kilometers, regular localization doesn't work, and even with what we've tried here, ATS was beating that, just because ATS really confines to the physical nature of the problem. And with ATS, you could increase the effective localization with no issue because you are not violating any physics. And because it's a new concept, we wanted to test. Now it's not entirely new. In reservoir engineering, in petroleum engineering, you will find this kind of localization along, different kind of fascies or something in the subsurface. But the fact that you are working with streams here is definitely more delicate. So we wanted to do some sensitivity analysis to see, how does this localization work? So we tried different localization radii, 50, 75, 100, 150, and 200 kilometers. And I'm showing here just the, I think, the RMSE at different gauges. And the observations are in black markers. And just, just for good measure, I'm also showing in dashed line the no data assimilation. So just this is the model running freely as an ensemble, but with no data assimilation. So yeah, again, I want to reference what Michael mentioned. If you remember his plot for the localization, where it looks like kind of for larger localization it's bad, and for small localization it's also bad. And that's what we've seen here. For instance, with 50 and 75, it's not as good because there's not enough information in the system. And in fact, if you check this gauge, the 50 and 75 is matching the no DA, so there's not much impact. And with 150 and 200, you are obviously going back to spurious correlation. It's not as good. For this case, the optimal scenario was with 100 kilometers. And again, because we've never worked with this kind of localization before, we also looked at different correlation functions. So we usually work with Gaspari cone, which is the kind of Gaussian-like shape. And I just wanted to compare with the different functions. For instance, what happens if I just take everything and weigh them the same weight, which is 1, rather than, so the weight does not decay, or this kind of linear decay, after half width. And I'm plotting, so I'm comparing a time series of the gauged observation with the predicted stream flow for all the gauges here, for the 3 different configurations. And I'm plotting them on this kind of Taylor diagram. I'm not sure if you're familiar with that, but so this is where you put kind of different information in one plot. So looking at standard deviation, the correlation coefficient, so how much your prediction is is correlated with the observation, and also the RMSE in here. So this is normalized. So ideally you would like to be as close as possible to the observation, where you have 0 RMSE, 1 standard deviation, and 1 correlation coefficient. So overall, we found that Gaspari cone, no surprise, was the best compared to the others. So we pick that, and we conduct all our assimilation experiments using this kind of function. So 100 kilometers and Gaspari cone. Okay. Let's see. Okay. So beyond sampling errors, beyond localization, you always have this problem, which is variance underestimation with that happens, in ensemble filters. There are many reasons for that. Just to mention a few. So your variance could be underestimated because of sampling errors, modal biases, high nonlinearity that you're not accounting for, non-Gaussian features, or errors in the data that you're not considering the correlations in space or the correlation errors in time. To me, all of these things combine together to cause some variance underestimation in the system. Now, how do I account for that? Simply by variance inflation. So this is just multiplicative kind of covariance inflation. So this is your ensemble members, and this is the mean, and you inflate them that way. And just to clarify the notation here, so F/A, I just think about it as forecast or analysis, depending on what your preference. You want to inflate the forecast ensemble or the analysis ensemble. Or you could do, as Laura was showing, inflation in the observation space. So you inflate R essentially. Yeah, so if you do that for the members, this end up scaling the full covariance matrix by a lambda factor in here. You know, and as a brief schematic here. So if you think about, if you start with the, let's think about the temperature, for example. Yeah, it's a very cold temperature if you think about Celsius, but yeah, it is what it is. So if your observation is like around freezing, for instance, here, this is the observation likelihood, and you are working with some ensemble. So this is the prior. This is your estimate from the model, and this is your mean estimate. You're obviously overestimating the observation. If you do just simple Bayes, you will end up with this green kind of posterior, which is in between the likelihood and your prior. Now, what happens if you inflate these samples? You end up with this kind of inflated, you know, more fat prior distribution. And if you go ahead and multiply this dashed reddish curve with the blue one, you'll see that your posterior actually gets closer to the observation than the uninflated version of that posterior. So it's a very simple trick. It works pretty well. We apply that in many different systems, in many different, mainly atmospheric applications. Over the years, we've seen that the ocean doesn't like so much inflation. Perhaps you've seen that from Francois's slides. You see how these kind of different layers in the system are, you know, have different kind of pressure density, you know, characteristics that they don't like to be disturbed that much. That's not the case in the atmosphere, and as we will see in this streamflow application. Okay, so we've seen what inflation is, and then the question is how to choose, what to choose for this inflation. Here I'd like to talk about this algorithm, which is a spatially and temporally varying adaptive covariance inflation algorithm. And the whole idea is that, you know, I don't know what this factor is. So, okay, let me assume it to be a random variable, and I'll try to use the data to estimate this this lambda or this random variable as I go at every point in the domain, you know, using the data. We apply Bayes rule. So we assume that we have some prior estimate of the inflation, which is P lambda here. So this is a PDF, and we construct some likelihood for the inflation using the data. And if we are successful, we multiply these two things together. We get a posterior for lambda, and we update lambda as we go. Now, in this schematic that I'm showing here, so the prior PDF for the inflation is an inverse gamma distribution. So you see there's zero probability, very close to zero, and it grows, and then, you know, this kind of skewed shape that you can see here. The likelihood is a Gaussian function, but it's a very messy likelihood because it's a Gaussian in terms of the data, but not in terms of lambda. So if you this is based on so if you build up your innovations as the difference between the observation and the ensemble mean, and you follow some innovation statistics from the literature, you construct this likelihood as with this mean and this variance. You'll see that the variance, or in the denominator in the Gaussian PDF, you have this lambda here. So it has a very weird shape if you plot that in terms of lambda. Now, if you multiply the red curve with the green curve here, you end up with this updated posterior value for lambda, and you can maximize the curve and find what's the value for lambda in here. And just to clarify what this thing is, because obviously this is perhaps maybe a lot of math, and it's not clear how this algorithm works. I'd like to show you here a very nice illustration of how the algorithm works. So this is a kind of a GUI that we provide also with the Dart software. We call it a Dart lab because it's based on MATLAB. And sorry, I feel like we live in a dinosaur age if you use MATLAB these days, given how Python is powerful and the Jupyter notebooks. But hey, it works, and we use it for education and illustrative purposes. So you can see there are many switches and buttons in here. So this is a Lorentz 96 system. We are running initially with no data assimilation. You'll see after a couple of time steps, the uncertainty starts growing. So all you can see here, the green are ensemble members, and the black curve is the mean, the ensemble mean. You'll see that we have the RMSE and the spread here, some rank histograms, if you're familiar with that here, and the many different switches. Now we are turning on data assimilation. And you'll see that we're assimilating a bunch of different observations, and you'll see that the inflation is growing in space differently, and it changes in time. And see nicely the members are closer to the truth. Sorry, did I mention the mean about the black curve? That's the truth. And you'll see how the RMSE and the spread matching each other nicely. And you can see when the system is okay, the algorithm, since it's adaptive, it just doesn't inflate much. Now, what I'm trying to do here is I am adding a lot of model error. So I am running the forecast model in the system with a forcing of 12, while the truth in black has a forcing of 8. And you will see that because the model is so biased, we will start drifting away from the truth. And you'll see how the adaptive inflation will respond to that. Once we are starting to drift, for instance, here, you'll see that the inflation is trying to inflate the members in order, to give some room for the algorithm to correct and bring it back to the correct trajectory. And because there is a lot of bias, so you see that the RMSE is increasing, but still you are not diverging. Things are so far somehow under control. Inflation is, doing a good job. Okay, so now what I'm trying to do here is just a switch to turn off inflation and see what things happen, what happens. So as you can see here, there's no more inflation anymore. And we are still working with a bias system. And let's see what the ENCAF on its own, we're still doing localization here, but the ENCAF on its own, how it works. And this is with 20 members, by the way. Yeah, so we're starting to lose the truth a little bit. And you can see there are some signs of divergence. The RMSE is increasing, the spread is decreasing, rank histograms are being skewed. You're getting these kind of U-shaped rank histograms. And we are at the point that we can't take it anymore. So let's turn back inflation on and see if it could bring us back from this misery. I'll see now inflation starts growing where in locations where it needed to grow. Okay, so we kind of brought back the RMSE closer to the spread. The spread is increasing back again. These are almost on the same order now. You'll see now at some point that even with a very hard bias model, once the inflation did its job, it will go back to almost no inflation, once everything is back to where it should be. And that's how it works. Okay. Now, one more question here before showing some results and from the streamflow system. What to inflate? We're working with the prior, or as I mentioned at the beginning, you can inflate the prior ensemble or the posterior ensemble. The question is really, it depends. It's more common in the literature to inflate the prior covariance. But just to illustrate that quickly, so here is a Lorentz 63 system. This is what Gare mostly used in his slides. And I'm showing different scenarios. So going from left to right, I'm increasing sampling error. So this is running with 5,000 members, and this is only with 5 members. And going from top to bottom, I'm just adding model errors. So this is like the best case scenario, no model errors, no sampling errors. And I'm comparing prior inflation only with blue, posterior inflation in red, and both actually prior and posterior inflation in black. And you see that without model error and with no sampling errors, really posterior inflation is the best in here. As we add some sampling errors, posterior inflation is still the best, beating prior inflation. And in both cases, doing both prior and posterior inflation actually gives you the worst results. So it looks like you're injecting unnecessary uncertainty in the system when you don't have a lot of model errors. Now, things really change when you add model errors. With no sampling errors, you'll see that posterior inflation is just really bad. Prior inflation is much better, and actually, if you look at that, adding both of them gives you the best results. And the same here, even with high sampling errors, where we saw the posterior inflation is the best, when adding model error is just really bad. Prior inflation is the way to go, and it looks like adding both of them together gives you the best results. So to me, we have a study on that comparing these two algorithms. To me, posterior inflation really deals with issues in the analysis step, like sampling errors, regression issues. But when you are working with model errors, really you have to tackle the issues in the forecast step, and where you have model errors, and that's where prior inflation comes into place. Now, is that the case all the time? I don't know, but this is my assessment of these two algorithms. Okay, so back to the stream flow stuff, and when we apply inflation, and so I'm just showing here a time average stream flow prior inflation for stream flow on the left, and the other state, which is the bucket here on the right. We are observing directly stream flow, and hence you see larger inflation than the bucket in here. And because we are doing ATS localization or along the stream localization, you end up again with the similar shapes for inflation, with similar tree-like shapes here. We had I think we had the most kind of a large density of observation of gauges in this region. So this is where you have the largest inflation compared to the rest of the region. Okay, and to put everything together, because stream flow is a positive quantity, you've seen this a lot in this summer school so far. So we need to make sure that the data assimilation framework produces physically meaningful update. We apply Gaussian anamorphosis. So quickly, so this is a skewed distribution for stream flow. If you do a simple ENCAF update, you end up with this kind of distribution where you have some negative stream flow. So you either have to deal with that, either you truncate them, you make them to zero. But what happens is that you're losing a lot of spread, and it just, it's not nice. It's not a healthy system. Now, we do anamorphosis, either empirical, where you construct the CDF, you invert, and you do all the things, so you end up with a Gaussian space. You do the update in the Gaussian space, and then you project back. Or you could do some, some analytical functions, for instance, the logarithm, which does a great job. It doesn't give you a perfect Gaussian, near Gaussian stuff. You update and you project back, which these two distributions look a lot similar to this one than this one. So. Okay, so in the last section here, Michael, do we have questions?
Yes, before we begin, maybe you have accumulated some questions you can answer. I think I'm going to start with the most recent one, because we just talked about the inflation. Christo asked if for the adaptive covariance inflation, what is the motivation of choosing that inverse gamma distribution for the prior, and is the posterior also an inverse gamma under these assumptions?
Right. Yeah. Thanks, Hristo, for the question. Very good, excellent question. So, the motivation here is that inflation is usually a number that you think about is larger than 1. When it's smaller than 1, you are deflating. There are some scenarios, where you need deflation, but that's off topic right now. If you do, for instance, simple Gaussian, you will see that you will end up with a shape that doesn't fit the quantity of inflation itself. In fact, Jeff Anderson introduced the scheme earlier in 2009 with the simple Gaussians, and I kind of changed the algorithm a little bit, and I thought working with inverse gamma. Or if you look at Patrick's stuff, for instance, where it's an inverse chi-square, which is similar to this kind of stuff, it behaves better than Gaussians. Hope that answers the question. And for the posterior, sorry, I forgot the second part. The posterior has a similar thing. Yeah. It's just the formulation is a little bit different here. Again, you could refer to this paper to see the formulation for the posterior, but the shape of the distributions are the same.
And another question about localization is that you're only allowing observation impact to within the individual catchments. So when you have observation from the other catchment, it does not impact the current one. Is that going to sacrifice observation info content? Meaning that if you have information about the current catchment, but it's farther away, so it goes out of the range, it's not going to be utilized.
Right. And that's a big issue. And that's what the issue that I refer to in hydrology as ungauged basins, which are the basins that they don't have gauges in them, how to update them. So yes, in the current localization, we don't update ungauged basins simply because, as I mentioned, it doesn't make sense because these catchments follow different regimes. One of the things that USGS is interested in is actually a study where to conduct some sensitivity studies to see where we have to put the gauges, minimize this issue of ungauged basins. But so far, you're right, you're correct. Two different catchments, observation in two different catchments do not talk to each other.
Okay, thank you. Krista also had an earlier question about the channel and the bucket model. Mm-hmm. How do they differ in functionality?
Yeah, so the channel is obviously has a lot more sophisticated physics. The groundwater bucket model is super conceptual. It's just if you think about it, it's a bucket model where a groundwater fills the bucket, and when the bucket is full, it starts flowing inside the channel. However, streamflow, there's a lot of more physics happening over here. You have to see how the water is moving in the channel. You can look this up online. This is the scheme, the physical scheme that is used to model the streamflow in the channel, but it's definitely more sophisticated than the bucket. Bucket is super conceptual.
Yes. There are two more questions, but it's more general. I think we can reserve them towards the end to ask them, and now you can continue to the results section.
Sounds good. Michael, I have 20 minutes, right?
Yes, we are fine until 4 o'clock. Yes.
Okay, awesome. Yeah, this shouldn't take long. Okay, so some hydrological assessments, some results in here. So, so I'm looking at the map of the stream flow on September 17th at some time. So this is the posterior that I'm getting from my data assimilation, and what I wanted to check, like if I want to compare that with the prediction of the model alone, which is the open loop. So I subtract this from the model prediction at that time, and I end up with this map. So it turned out that the rest of the domain is okay, but at this river, which is the PD River in South Carolina, the data assimilation is adding a ton of water, as you can see here. So around 6,000 cubic meters per second, which is quite surprising at when we saw that. And we wanted to look at this more in detail. So we actually picked up a gauge in here, and we tried to look at the hydrograph. So this is the hydrograph. On top of the y-axis here, on top, according to the right y-axis, I'm plotting the precipitation that that gauge is seeing. And in the bottom, this is just the model prediction. Now, if I put on top of that the observation, so this is the real-time gauge observations of the stream flow. You'll see that after landfall, the gauge is super flooding, but the model is not seeing that. And that's probably because of some errors in the precipitation that were assigned there. Now, in our HydroDart system, the prior ensemble and the prior ensemble mean is highly improved compared to the model. And in fact, if I plot the posterior is almost matching the gauged observation over there. And to understand this further, I will plot on top of that the inflation that the algorithm is providing me. You see that once the algorithm see the large discrepancy between the observation and the data, it start kicking in the inflation until it improves the prior and eventually brings a very good accuracy in the posterior. And you'll see afterwards, once you are close to the observation, the algorithm goes back to 1 turns off inflation. So I mean, if you look at it, this is a massive improvement over the model estimate. We also looked at the same gauge here. So this is the rank histogram. So this is the open loop stream flow. Or maybe this is a gauge close to it. I don't remember exactly. As you can see, so the rank histogram from the open loop or the model prediction on its own is highly skewed to the right, meaning that the observation stream flow is larger than what the model is predicting. With the prior from the data assimilation scheme, so this is the prior ensemble, you see that you nicely get this kind of, not really flat rank histogram, but which really tells you that the observation is falling within your ensemble members and not outside your ensemble. And that in statistical terms, or you will hear people in the community, in the DA community, saying this kind of words. The observed something is statistically indistinguishable from the prior ensemble. So if you pick any ensemble member from your ensemble, it should be statistically indistinguishable from your observation. Here, unfortunately, things are not looking good. The observation, tends to fall outside the open loop ensemble. The probability for this to happen is larger than 50%. So just for the sake of visualization purposes, I didn't put the entire extent of this bar here, but it's very long. So the ensemble is way far from the observation. The other thing I'll show here also the effects of inflation. So showing just for one gauge, the hydrograph or the time series of the stream flow. On the left, this is an adaptive prior inflation only, and on the right, this is an adaptive prior and posterior inflation. Just to see how things, how these two different approaches differ. In crosses, that's the observation. Now, when it's green, it means that the data assimilation system have used it. When it's red, it means the data assimilation did not use it, just because it's far away. And this is a kind of a switch that we have in Dart. We call it outlier threshold, or QC, kind of quality control. So if your observation is far enough from your ensemble, we just don't assimilate it, because it will crush your spread if you assimilate it, and you will be stuck afterwards. So what I would like to focus in here is, if you check the falling limb of the stream flow here compared to this one, you are better fitting the observations. In fact, you are rejecting less observations. So you are rejecting 9% here compared to the 15% in this scenario. And again, looking at this, and just to make sure I'm not showing the posterior inflation wrong, because it's just bad. Posterior inflation only does not work. You need prior inflation for things to work. Now, when you add these two things together, one might argue that posterior inflation could be resolving other regression issues, such as sampling noise and non-Gaussianity. But on its own, posterior inflation is no good. So the other things I'd like to show here, so some results, some also hydrographs with Gaussian anamorphosis. So on the top, so this is some gauge with the standard data assimilation update, and here we use some transformations. So if you look at the distribution of your prior members, when you do Gaussian anamorphosis, you kill your higher order moments where they are non-zero in this scenario, and you fit better the observations. For instance, here the rising limb of the hydrograph. And this is especially important because at this point where some members are flooding and some others are not, this is where anamorphosis plays a good role. And overall, we find better estimates with higher skill when doing Gaussian anamorphosis. Now I have to say that, this is not the scenario on all the gauges. Some gauges really did not like so much Gaussian anamorphosis. In some gauges it worked, in some it did not. It's not a black and white that this works and you should be using it everywhere. And things need to be investigated, which I'm currently doing at the moment. You're looking at different functions. You're looking at empirical formulations for Gaussian anamorphosis. One of the things that you find rarely discussed in the literature about Gaussian anamorphosis is that when you transform the observation, you have to also deal with the observation error for this observation. How do you transform that? So things are tricky. Yeah, and the last thing I think we've done is, what happens if we withhold some observations just for validation purposes? So instead of assimilating the entire 107 gauges, I guess we withhold, I don't remember, like 10 of them or something. And then we compare, we look at the performance at these withhold gauges because we have their observations, so we know what's the truth. And again, I'm looking at two gauges here. So this is the observation in the red, what do you call that? The red axis, the gray axis. The open loop in both scenarios. So the open loop. So this is observation minus prediction. So the open loop is overestimating the values. In the blue curve, this is when we assimilate them. So this should be the best case scenario. And in the green, this is only when we withhold them. So this is the information coming from other gauges, essentially. So really, data assimilation is able to spread the accurate information even to unobserved locations, as you can see here. Okay, so this is my last slide, and here I'd like to talk about some future research directions, some stuff that we are doing at the moment. We're actually starting right now a full CONUS streamflow reanalysis for the past 30 years. So we're not looking at a simple subdomain as we saw in this study, but rather a full streamflow reanalysis for the entire CONUS domain. And in that, I'll be exploring some other approaches, not only NCAR, like a hybrid kind of NCAR variational approach based on a recent study where it's kind of a nice adaptive formulation for a hybrid scheme. And the other project that we will be starting in the summer is one interesting thing is on top of assimilating streamflow, the gauges also that USGS provide temperature observation. So about the temperature of the water, and the question is, can the temperature data improve streamflow? So if you just imagine that the groundwater is usually colder than the water in the channel. So when groundwater seeps into the channel and the water starts getting colder, you will understand more how the stream flow is flowing. So we would like to investigate that. And also the thing that I mentioned is the placement of the gauges. Where should we place those gauges? And the last thing down the line is we would like to couple the land surface model with WRF hydro and assimilate not only stream flow, but soil moisture, and look at different weak versus strong coupling when we assimilate into these both of these models. And one of the collaborators I mentioned on the first slide is already doing snow data assimilation with WRF hydro, so that's also in the works. And with that, I'd like to stop and take questions.
Thank you very much, Moha, for the presentation. We have two more questions left in the list. One is quite particular in when you mentioned that the localization breaks the base rule. And
sure.
Can you elaborate what do you mean by that, and how does it break it?
Right. Yeah. Again, you don't see that much.
Let's go way back.
Right. Yeah. Unfortunately, I don't have base rule, but if you think about base rule as P of xy equal to P of x times P of y divided by x, this base rule is telling you that all the observations that you have at the moment, if you condition your state based on all of these observations, you end up with some posterior. Now, localization is actually limiting that, is saying that I have all these observations, but I'm not gonna use all of them in the update. So in a sense, the assumption that you started with when you do localization, you are not following, the basic equation that you started with, if that makes sense.
And yeah, I can follow up on that. I think you can also look at serial algorithm. It is exactly equivalent to the full matrix version without localization, because
Right.
now you point-wise multiply the common gain with some tapering function, and you sum these impacts together. It's no longer equivalentable towards the full matrix.
Yeah, there have been many studies in the literature that, well, maybe not so many, but I think the best one was by Lars Nerger, it's studying the impact of serial assimilation compared to batch assimilation. And I guess that the take home message was from that study that the difference between assimilating serially and assimilating in batch is not so big, and it's not quite clear if which one is better than the other. Again, as Michael mentioned, with no localization, these two have to be equivalent, but with localization they are slightly different.
Well, I guess there will be some debate always on the methodology. I think we can discuss, if you don't agree with what we said in the answer, we can carry on the discussion in this thread. I had an earlier question on the sensitivity or location of these precipitation events. So if your atmospheric model does some bad job in producing precipitation event, especially when it's quite chaotic, does the water cycle component suffer from that and lose predictability?
Indeed.
Yeah.
So that's actually what I can what we've seen in this gauge. In fact, the precipitation here is just bad. There is way more precipitation happening than what the weather forcing component is giving us. And as you can see, I mean, the model physics is quite robust, but just it's responding to the precipitation, and there's not much water coming in, so the model is just bad. Now, on this gauge, inflation somehow helped, but I can tell you on other gauges there are 107 of them in the domain. Just inflation could not, it's not magic at the end of the day. So you're right, Michael. If you don't get the precipitation well, you're not in a good shape.
Yeah, so we still need synergy between different modules.
There you go. There you go. I mean, ultimately, if you couple everything together, then that's the goal. But that's very expensive and very tricky and hard.
Okay, you don't have any more questions right now in the list. Anything from the audience right now? Before I let Mohab go.
I'm happy to stay. If you...
I think, yeah, nobody is appearing to be typing anything.
Okay.
So I think it's a good time to close. I guess today's sessions are quite interesting. Personally, I find I learned a lot from all these. Thank you for all the speakers for presenting the work, and I really enjoyed it. And thank you all the participants for the nice discussion.